In our previous examples, what we did is we learned that the derivative represents the slope of a curve, and we can evaluate that at a point. And then we also learned that the area under the curve represents the integral. So one finds the slope, and that's the derivative. And then the other one is where you start with the slope and you work backwards. So the derivative and integrals are kind of inverse operations of one another. So example number one in your textbook, everything we're going to do today is on our calculator. Example one in your textbook wants you to find the derivative of x cubed. Now, if you go to evaluate it at a specific point, so if I hit second catalog, and we can scroll way down to n, but that would take a really long time to scroll all the way down. So one thing that you should know is that these little teeny tiny green letters here are, well, you can jump to that letter. So if I go to, say, if I click on this button here right now while I'm in catalog mode, it'll take me to the ends. So there's a little N right over here, green letter. Now it depends on what kind of calculator you'll have. It'll be a different color. You know, it might be blue, it might be purple, depending on your, but it's in the upper right hand corner of the buttons. Now that I'm in the N portion of the catalog, I'm going to go to N derive. Now this is a tricky thing because what we need to do is the first thing we need to do is enter in the function. So the original function that we want to find the derivative of is x cubed, or x raised to the third power. So keep in mind that your calculator is like a computer and it runs on a program, but it's not a sophisticated program like a real computer that you guys are used to. So first thing I have to do is enter in the function. Then I'm going to hit a comma. Then I have to let the calculator know what variable I'm interested in having it do the calculations. And so I'm going to choose x. Then I hit comma. And then I need to figure out exactly what x value I want to evaluate the curve at. So I'm going to enter in 2. When I'm done, I close the parentheses. And what this is saying is take the derivative of the function x to the third power when x equals 2. All right? So I'm going to hit enter. Now this does this, there's a definition of calculating. Remember that one day when I said we could do 2 and then use the point 2.1? And I said if we wanted to become more precise, we could say 2.01. And then we said we could do 2.001. Well, the calculator, that's basically what the calculator does. And so, but it goes 0.001. And so this is the answer we get calculating the slope between the 2 points, x equals 2 and then x equals 2.001. What is the answer, though? It's actually 12. Now we can see that if I go in here and I graph this, x cubed, and I hit graph, that's what the graph looks like. And what we're interested in knowing is what is the slope of the tangent line at x equals 2. Well, we could also do this while we're in graph mode. So if I hit second calc, and then I go down here and see where it says dy dx, that's another way to write derivative. It's actually the derivative of y with respect to x. So I'm going to hit enter. And then I just have to plug in the x value I want to evaluate. So the last time we wanted x equals 2, so I'm going to hit x equals 2 by selecting the number 2. And when I hit enter, guess what? It's going to approximate it at that 12.01. Or 12.000001 or whatever it is. Okay? Does anybody have any questions on that one? Nope. Okay. So that's what we do. But we all know that that 0.001, we kind of toss that out. Okay? But I guess when you think about it, though, if we were to round this to, say, 3 decimal places, we would toss that 0.000001 out anyways and round it to 12. Let's do another example. That was example number 2. Or I mean example number 1. We could do the same thing on our calculator with regards to the integral. So that calculates the slope. When we do the integral, it actually calculates the area under the curve. So this time I'm going to graph the function first and show you how to do it, and then I'll show you how to do it algebraically. So I'm going to change my function to 1 over x. So I'm going to say 1 divided by x. And that's the graph that looks like that. And now what I'm going to do, and I'm going to zoom in just a little bit. Well, I want you guys to see what we're doing. So that's what, well, let me manually enter it in because I want to go from 1 to 4. So I'm going to say 0 to 5. And I think everything else is fine. Okay. So that's what I want to look at. And I want to find the area under the curve from 1 to 4. Now that means that we're going to integrate. So what we're really talking about mathematically is that we have the slope, which is 1 over x, and we want to work backwards and figure out what the original function was, evaluated from 1 to 4. So this would be finding the area under the curve if we were to draw a line here at x equals 1 and then another line here at x equals 4. Now the calculator will calculate that for you once you enter in the function. Go down to the integral symbol there, and that's the integral of f of x dx. When I choose that, the next step is to enter in the lower limit. In this case, it's x equals 1, and then we're asked to find the upper limit, which is x equals 4. And then when I calculate that, what it does is it goes through and it uses that rectangular approximation method with a very small increment. And it's an approximation, but it's a very good one. So the area under the curve from 1 to 4 is 1.3862944. Okay? Now, that's what we're used to seeing and doing, but you can also do this in the calculator. So if I hit second catalog, and this time the function is actually f, it's the function NIT. So it starts with the letter F. So I'm going to go to A, B, C, D, E. Is this F? Yeah. And we want to go to this one right here because it's the function integral. That's what FNINT stands for, function integral. Just like before, we're going to have to enter in the function, which is 1 divided by 4. Oh, not 4. 1 divided by x, comma. Except now it's just a little different when we enter it in. We want to evaluate which variable, x, and we want to evaluate the lower limit of 1, comma, to the upper limit 4, and that's pretty much all the information that we need. And so now when I hit enter, I get that. It's a little different, yeah. On the last one we had 944, and you can see that the calculator rounded, but most of the time, on the AP Calculus exam, you're going to round to 3 decimals anyways, so it's pretty good. You can actually write commands and make adjustments to that, but this is a fairly accurate approximation. Okay, any questions on that? So now what I'd like to do is I'm going to clear this out. Now, if I hit graph, here's the funny thing about once you calculate the area under the curve. If I clear the function out, it should take away my area under the curve. However, sometimes it doesn't. If it doesn't, you can hit clear home. And what you would do is you would go into the catalog, you'd go to C, and you'll see this thing where it says clear draw. It literally draws that area under the curve. And if you click on that and hit enter, it'll clear it out, but it's already cleared out, so it wouldn't do it. So now let's look at example number 3. Example number 3 says an automobile is driven at a variable rate along a test track for 2 hours so that its velocity at any time from 0 to 2 hours is given by the function f of t equals 30 plus 10 sine of 6t miles per hour. Wow, that was a lot. So the velocity was calculated at 30 plus sine of 6 times t, but I'm just going to plug in x. That's fine. All right. And then for my window, I'm going to do the zoom format for trig because that's just well, let's do Zoom Fit. Zoom Fit usually does a pretty good job. All right, there it is. Now, the question is asking, how far did the car travel in the 2-hour test? Now, when you look at that, you'll see that it travels, when you look at that, you'll see that it travels a greater distance, then it comes back a little bit, and it comes back and comes back and comes back. What we really need to do is we really need to find the area under the curve, okay? I'm going to zoom out a little bit so you can actually see the area under the curve. So this function represents the velocity of the car. So you see the velocity increases, then it decreases, then it increases, then it decreases. It probably has to slow down to turn the corners. Okay. And so you'll see something like this. All right. Now, if I let the variable go from 0 to 2, I can find the position of the car. In other words, how far did it travel by integrating this or finding the area under the curve from 0 to 2. So if I hit second, trace, come down here to the integral symbol, find the definite integral of f of x, hit enter. My lower limit is 0. My upper limit is 2. Now what this will do is the area under the curve of the velocity function actually represents the distance traveled. So as soon as I hit enter, I'll see that I traveled 60 units. And so since the information was given in miles per hour, that means that I traveled 60 miles, 60.260,243 miles in 2 hours. And that would be kind of hard to calculate. And that's why we really do this. A car never really just drives at 40 miles per hour nonstop without fluctuating its speed. So when this car slows down and let me zoom in on that so you can see the area under the curve, the x-min would be 0 and the y-min would, or what did I evaluate that, 0 to 2? And then our y-min is 0, and then this was like 30 plus 10, 50. This will be a better graph. Okay, so that's what we were looking at. And then when we calculated the area under the curve, if I hit second calc, I'll do it again so you can zoom in on it. The area under the curve represents the position or the distance that you traveled. So from 0 to 2 hours time, we traveled 60 point something something miles. Okay, does that make any sense? All right, let's do example number 4. Example number 4 is basically the same thing. Finding the derivative from data. So let's move ahead to example number 5. Let me read example number 5 to you. It says this example also uses ball data. So in example number 4, there was data given of a ball falling. This is pretty much kind of what Newton did. So in the data, they give us the time and the position of a ball as it free falls. And then we can use the position over time. What is position over time? Does anybody remember? That's velocity, right? So we're given the velocity, and then in example number 5, what they'd like us to do is to kind of just model the velocity. Like we need to calculate the velocity, and then example number 6 wants us to go the opposite and figure out how much distance the ball traveled in that time. So let's do that. So what we need to do is we can go into stat, edit list. Mine's already blank, and I'm going to enter in the data as it is in the textbook. So this is on page 829, and we have 0.04 is the first time, 0.08 is the second time, 0.12 is the third time, 0.16 is the fourth time. Oops, you guys are supposed to help me out and let me know when I make a mistake. And so I'm not going to do the whole thing. I'll just do, this will be the last one. And so what I did, this is all the times listed Now, next to that, at 0.04 time, the ball was actually 6.8 meters, or 6.8 feet high. And then at 0.8 seconds, it was 6.4 feet high. And then at 0.12, it was 5.95 feet high. And then at 0.6, it was 5.45 feet high. And then at 0.2, it was 4.9. Okay, so now if I go in here, and let's clear out this graph, and let's turn our stat plot on, make sure that's turned on. So I'm going to hit second Y. Let's turn that on. L1, L2. See how that says L1, L2? And then it's all gerbly gobbly in there. That's a real word. Yeah, gerbly gobbly. You guys haven't heard that before?
It's not a real word. What is it?
Gerbly. Google it. Gerbly gobbly. It's a complicated word. All right. So now clearly there looks like there's some sort of linear regression. So now here's what we need to do. All right. If this is a graph of position over time, the slope of the line is the velocity, right? From the data that I've entered in, it looks like a straight line, like a linear graph. So what I want to do is I want to find that linear graph. So one thing you could do is just hit hit stat and go to calculate, and then just find the linear regression. The linear regression by default does L1, L2, and as you can see, the slope is negative 11.87. So the velocity appears to be traveling at about an average of 11.875. Okay, now I did not enter in all the data. If you continue to enter in the data, it would have come to negative 14. That's what the textbook says. So from that point there, that's pretty much it. That's how you find the derivative, right? So sometimes you find the derivative by approximating or subtracting. You could do the slope of the first point and the second point, but to get a better a more accurate description, you could do it that way. Okay. Example number 5 goes on to give you more data. Example number 6 is another thing for data. If my slope is negative 11.85, how could I find the distance traveled in, say, a half a second? How could I do that? If this is the derivative, if this is the slope, how can I find the distance traveled? Use that number. So what I would do is I could graph negative 11 point, what was it again? I can't remember. 11.875. Negative 11.875. And we're going to graph that. And now I've got to turn my stat plots off for just a second. Okay, and now let's adjust our window. We're interested in a half a second, so we're going to let our x go from 0 to 0.6. What will be our maximum y value? Or I said that wrong. What would be our minimum y value for the graph? 0. What would be our y max? Oh, actually, you know what? I said it right. What would be our minimum? Negative 12. And what would our max be? 0. And so when I graph this, we're going to get something like this. We got a straight line here. This is the x-axis. What I want to do, if I want to figure out how far this ball has traveled in 0.5 seconds with a velocity of negative 11.875, I want to integrate. So if I integrate that, what would be my lower limit? 0. What would be my upper limit? No, 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 no. No. I want to know how far the ball travels from 0 to 0.5 seconds. So 0.5, right. And so that will give me the area under the curve. Now, it says negative 5.9375 feet. What does the negative represent? It's falling down, right? The ball's falling down. We have the ball up at a certain height, then we let go, and that's how it falls down. All right? That's it.